Hi, my name is Benjamin and this video is recorded for Math 203, Matrices and Applications. This is a course I took at the University of the Philippines, Diliman. Today we're going to talk about Markov chains and its applications to internet search engines. So let's start. I know that this is a linear algebra course, but I think it's important if we take a look at the probabilistic definition. So here's the definition. Uh, Basically, the most important part of this definition is the simplification assumption that Markov is providing us. Basically, it tells us that instead of the random variable x sub n plus 1 being conditional to all of its previous values, it is only conditioned on the value before it. So like what I've stated here, intuitively, this tells us that the future value of this random variable is only dependent on the random variable at the previous time point. So we will look at an example that will make this notion better for us. So this is the example from the book. Suppose that there are two competing television channels, channel 1 and channel 2. Both of them have 50% of the viewer market at some initial point in time. Assume that every year channel 1 gets 10% of channel 2 share, and similarly channel 2 gets 20% of the share of channel 1. So what I will do here is I will show you how we can implement the solution provided in the book in code and explain some of the important concepts along the way. So let me just open the notebook that we will be using for this lecture. Alright, so let me just go to presentation mode. So again, this is just the given earlier. And from this given, we are able to construct this system of linear equation. So basically, this says that x sub 1 of k plus 1, meaning the share of channel 1 at time point k plus 1 is equal to 80% of its current share. I mean the share at time point k plus 10% of the share of channel 2 at time point k. And similarly, the share of channel 2 at time point k plus 1 is equal to 20% of the share of channel 1 at time point k plus 90% of the share of channel 2 at time point k. So we are asked to find what is the share after 1 year and after n years. So to get the market share after 1 year, we can simply make use of the linear system that we have here. So here, as you can see, I denoted T sub 0 for the market share at time point 0. So both channel has 50% of the viewer market. And when we apply the formula from above, we get that after 1 year, 45% goes to channel 1 and 55% goes to channel 2. And this answer is similar to what was provided on the textbook. Now, but notice if we take a look at this linear system, notice that we can actually write this as a product of a matrix and the vector, and we will do that. All right, so basically, this matrix times this vector is similar to what we have seen from the previous slide. Actually, I made some typo here. This should actually be uh, x sub 1 of k. Yeah, just uh, just to be it more similar to what we have seen earlier. So again, going back, this product is simply equal to this linear system. And we call the matrix um sorry. We call this matrix as the transition matrix. Later in this presentation, I will show you how we can interpret this, yeah, in the next few slides when we look at a more practical example. All right. So, um, basically here I just converted the Python list into NumPy array. So NumPy is a library in Python that handles some linear algebra computations for us. So this is uh, the value at time point zero where both channel has both 50% of the market share, and this is the transition matrix that we've seen before. If you notice, it's presented almost similar to the LaTeX code from earlier. All right. So yeah, again, we just simply perform the matrix vector multiplication, and as we can see, the answer that we have here is simply similar to what we had when we computed it manually right here. So I hope that's clear so far. So now, since we have shown it using matrix vector multiplication, we can see that we can move forward. We can compute the value at time point 2 using the same formula from earlier. And again, as you can see, these results are equal to the answer that we have from the book. And we can see some sort of pattern here. Again, the value of the future time point is only dependent on the value on the previous time point. And in programming, we can actually write an algorithm for this to compute an arbitrary value for time point n. This is a technique called recursion. I'm not going to talk about this in more detail, but yeah, basically we will just implement in code the mathematical definition for getting the state at time point n. Right, so here is the code. Again, it looks really similar on how we implement it in math. So basically, we just say that whatever, if we are finding the value at time point n, it's related to the value at time point n minus 1. And as we can see, if we use our function and we pass it an integer, we get the same result from earlier slides, and as well same results that we have from the book. All right, so here is at time point 5. All right, and I will just make some manipulation so we can graph what happens to the share as time goes by. We are computing up until time point 100, so meaning after 100 years. And as we can see, if we look at the graph, at around time point 40, so meaning after 40 years, the share seems to stabilize. So again, this is similar to the result that was provided in the book. So as you can see here, the share for channel 2 after 40 years onwards is around 66%, and it's around 33% for um, channel 1. All right. But again, if we read further, we will see that there is actually a convenient result presented in the book, um, telling us that we can actually get the value at time point k by only considering our state at time point 0. And this convenient formula was introduced. So basically, it tells us that the value at time point k is simply equal to p raised to k times our state at time point 0. So this is really convenient, as we will see in the next few slides, that it will improve our code significantly. Again, P here stands for the transition matrix. All right, and then I just wrote it in code, the formula given from this slide. I wrote it in code. Um, and now we will see how knowing one theorem can actually make your code significantly better. So here we are calling our initial function. We are calling the function that we write using recursion. And as we can see, if we are computing the state um, of the random variable from time point 1 to time point 1000, it takes us around 3 seconds. But if we use the mathematical formula, we will see that it's not even close to a second. Oops, sorry. This should also be um, this should also be 1000, but no worries, as we will still see. It will. Oh, sorry. I have to run all of the previous cells. Give me just a sec. All right, it's running now. As you can see, the duration. As you can see, the duration, if we use the better algorithm, this takes advantage of the result that we've seen from the previous slide. Our code executed in less than a second. So again, this is really amazing and fascinating that knowing one simple fact from linear algebra can actually make our code better. And in fact, if we if we consider larger number of state, the recursion method will actually fail. So for example, if instead I wanted to calculate the values from time point 1 to time point 10,000, this code will actually fail due to recursion error and it will take some time. Okay, it's just running right now. It will just take a few seconds. Okay, so as you can see, it's still processing it. Yeah, but it will give us an error in a few seconds. Any second now. As you can see, since the computer is having a hard time uh, computing this value, that's why it's taking a bit of time. All right, as we can see, there is a recursion error. But if we do that to the algorithm that uses the mathematical fact, we will see that it doesn't even take us a second to um, to show the result or to compute the result. You just go back to presentation mode. Again, another helpful question to ask is, as we can see from the chart before, the chart from earlier, the values seems to converge at some value. So is there a way to find on which value our state converges? As we will see in the next few slides, there is an analytic formula for this. But let me just show you how we can numerically compute for numerically compute for where the value will converge. So yeah, as we can see, this is using um, the numerical algorithm that I wrote here, and it this is similar to what we have seen in the chart, and again similar to what we have seen from the book. But again, it turns out that we have a theorem telling us that uh, if we raise if we raise the transition matrix to some large power n, it will actually converge to a matrix where the column vectors of this matrix is equal to the vector where our state converges. So to make that more concrete, again, let's look at the chart from above. As you can see here, channel 1 converges to around 33% and channel 2 converges to around 66%, and we can verify that by uh, computing the state at around 40. I could have used better algear, but yeah, let's just use get state since it's a small number. As you can see, yeah, this number is close to what we have found when we do the numerical solution. And again, a simpler way is to just make use of the theorem. And as we can see, it does converge to a matrix where the column vectors are um, where our state vector converges. So let's go back to presentation mode and let's look at an applied example. So this is a dataset from Vega datasets. It's another Python library. So basically, it gives us weather information by day. But the column that we are interested in is the last column. It gives us a word description on what is the weather for the day. So for example, on January 2nd, it's raining for a few days. All right, and we will just do some manipulation. As you can see, if we summarize the dataset, most of the days it's sunny, it's foggy, it's rainy, and the other two weathers have significantly lower counts. All right, and we will just do some manipulation, and we will arrive from this transition matrix. So basically, what this transition matrix is telling us is the probability that it will rain tomorrow, given that the weather today is drizzle, is around 27%. And as we can see, as a sanity check, if we look at the diagonal of this matrix, so for example, the probability that tomorrow it will be foggy, given that today it will be foggy, is 61%, and it is the largest in this column, which makes sense, right? So if it's sunny today, you would expect that tomorrow it will also be sunny, as we can see here. And similarly, if it's sunny today, the probability that it will snow tomorrow is significantly lower. All right, and then I just converted that formatted data frame into a NumPy array. Again, we can think about it as a matrix. And then I rewrote the getState function to use the mathematical formula and to also the initial state to be accepted as a parameter, as well as the transition matrix. And as we can see here, since this is this is an actual data set, we don't know what is the initial state. So like a reasonable assumption is drawing from a uniform distribution. So we're like saying that the it's equally likely that it's either raining or sunny, the weather at time point zero, so at the beginning of time. So I think it is quite a reasonable assumption. So we draw from the continuous uniform distribution, and I just made some modification to ensure that what we get is a probability vector or a random vector. Okay, and as we can see, if we use our getState function, it tells us that after 3 days, here are the probabilities for the respective, excuse me, for the respective weather. So the probability that the weather tomorrow is drizzle is just around 4%, which makes sense based on the raw data that we have when we counted the occurrence of each weather types. All right, and again, I will just write some manipulation so we can look at the graph. So as we can see here, it's expected that the highest probability goes to the sunny type of weather, since again, as we seen from the data, it has the largest number of occurrences. As we can see, the interesting part here is that initially rain has a higher probability than fog, but as time goes by, it seems that fog has a higher probability than rain, because if we go back to the count data that we have here, if we go back, as we can see, fog has a significant number of records compared to rain. So yeah, I think that's it for the introduction to Markov. On the next video, we will talk about its application at internet search engines. Thank you.